this video, we're going to talk about basic probability rules. So a probability model is a description of some chance process that consists of two parts: a list of all possible outcomes and the probability for each outcome. Now, this is probably one of the most missed questions on a quiz because it's got two parts to it here. Most of us forget that we have to list all of the possible outcomes. Those are called the sample space. So we got to come up with what's in our sample. A probability model does more than just assign a probability to each outcome. It allows us to find the probability of a certain event. And we talked about events the other day. This is a collection of outcomes from some chance process. Okay, so to find the probabilities of equally likely outcomes, so nobody is cheating on these, if all outcomes in the space are equally likely, the probability that event A occurs can be found using this formula. So the probability of A is the number of outcomes in event A divided by the total number of outcomes in the sample space. Now, the other day when we were talking about it, we called this successes over total. So suppose you flip a fair coin 3 times. A fair coin is one that's just not loaded, which means nobody's trying to cheat on the coin. One side isn't heavier than the other. We want to give a probability model for this chance process and then define event A as getting exactly 2 heads. Okay, so first thing, remember with our probability model, we have to come up with our sample space and then our probability that it will happen. So if I'm going to flip a coin 3 times, so I could get 3 heads, I could get 2 heads and a tail, I could get a heads, a tail, and another heads, and then this is heads and then 2 tails. This is every combination that I can come up with, my first coin being a heads. And then what if my first coin was a tail? Well, we could have 2 heads, or we could have 2 tails and then a head, or we could have a tail, head, tail. I guess I switched these 2 around. It doesn't really matter though, as long as you get them all. Or we can have 3 tails. This is the only possible combination for us with flipping 3 coins that are fair. So there is our probability model. And then what is the probability of each outcome? Well, there are 8 outcomes, so our probability of getting any of these combinations would be a 1 out of 8. So I'm going to just clean this up so you can see it a little better. So this is what it looks like. And again, probability models got to have 2 things, the sample space and the probability of each one of the outcomes. So that's what our probability model looks like. Now, we want event A to be exactly 2 heads. So if we go back and look at our sample space, we want to find out where exactly 2 heads are happening. So I just flip back real quick here, and where are exactly 2 heads happening? Well, there's 2 heads happening here, 2 heads here, 2 heads here, and those are the only ones. So the way that we would write this, the probability of successes over total, well, we had 3 successes out of 8 total. So our probability that event A happens is 3 out of 8, or if we wrote it as a decimal, it would be 0.375. Our work so far suggests 2 common sense rules that have a valid probability model that must be obeyed. The first one we already know, all of the probabilities have to be between 0 and 1 inclusive. So that was not new to us. And then the second one is all possible outcomes together must have probabilities that add up to 1. So for example, if we were rolling a dice, a six-sided dice, they all have a probability of 1/6 happening. And when I add all those probabilities together, I'm getting 1 for an answer. So anytime we observe a chance process, some outcome must occur. Okay, here's one more rule. So we've got our 6 dice right here, but I want the probability that an event does not happen. So this is going to be 1 minus the probability that an event does occur. So let's say I didn't want to roll a 2. So the probability that it does not happen is 1 minus the probability that it does happen. So a 2 has a 1/6 chance of being rolled. So I just subtract that, and that will give me my probability that it does not happen. This is often called, so this would be 5/6 for our answer here. This is often called an opposite problem. We refer to the event not A as the complement, and we talked about complements the other day. Here is another notation, and it kind of just depends on what textbook you're using. That looks like it's an exponent, that's the position it's in, so A complement. This is the same thing that we showed you the other day about A naught. Those both mean the exact same thing. So this is the complement rule or the opposite rule. And it just says the probability of A complement is equal to 1 minus the probability of A, where A complement is the complement of the event. So the event A does not happen. So what does that look like? Let's suppose we tear into a bag of M&Ms and you pour one candy into your hand. You pour the candy into your hand, you observe the colors. According to Mars Incorporated, the makers of M&Ms, the probability model for a bag from its Cleveland, Tennessee factory is shown here. So the first thing is we need to explain why this is a valid probability model. And then after that, we want to find the probability that we don't get a blue marble. Okay, so first off, in order for this to be a valid probability, all of the probabilities have to be between 0 and 1 inclusive. So as I'm looking at these, all of these are between 0 and 1. So that's the first part. The second part is that all of the probabilities have to add up to 1. So grab your calculators real quick. And we want to know, does that equal 1? So 0.207 plus 0.205 plus 0.198 plus 0.135 plus 0.131 plus 0.124. And when we add those all up, we do find out indeed it does add up to 1. All right, so find the probability that you don't get a blue. All right, so we know the probability all adds up to 1, and I don't want a blue. So we're going to do the complement problem on this one and then just subtract out what we don't want. So we're going to take 1 minus the probability that we do want a blue. So we're going to do 1 minus 0.207 to get 0.793. That is the probability of not getting a blue. Now look at our notation here. Make sure you're getting that down. Now, would that be any different than me just going in here and adding all of these up? And the answer is no, it isn't. Those are going to be the exact same steps. But the probability of not getting a blue is a lot quicker than me having to add up all of those other numbers. Get you to the same place though. What's the probability that we get a green or a red? Okay, so the probability of green or red is just going to be the probability of a green one plus the probability of a red one. And if we look back on our chart, the green one had a probability of 0.198 and the red one had a probability of 0.131. So add those guys together, it should be 0.329. So that's our probability of getting a green or a red. These don't have any outcomes in common. which is basically saying that I'm not going to pick up one candy and it's going to be both red and green at the exact same time. And this is, of course, not holiday M&Ms that we're looking at either. So, or a specialty M&M. This is just a plain old bag of M&Ms. So you don't pull out an M&M and get a green and red one at the same time. These are called mutually exclusive events. They cannot happen at the same time. As a result, we can use the addition rule for mutually exclusive events. So make sure to jot this down. Pause the video if you need to. Two events, A and B, are mutually exclusive if they have no outcomes in common, and so can never occur together. So they're not going to happen at the same time. So the probability of A and B is going to be 0. They can't happen at the same time. I cannot pick an M&M out of a bag that's going to be red and green at the exact same time. That can't happen. So for this one, all we have to do is say the probability of A or B is equal to the probability of A plus the probability of B. So here we're dealing with an AND problem. Here we're dealing with an OR problem. Now, this formula we can change around and solve for different parts. So if I knew the probability of A or B, and I knew the probability of A, then I could solve for the other one, probability of B. You have 3 parts here. They're going to give you 2 of the parts. You just manipulate it so that you solve for the part that you need. And then again, this is the key thing here, just to remember, this only works for mutually exclusive events. So we're going to get into it a little bit more in the next section, but mutually exclusive, they cannot happen at the exact same time. Okay, suppose you have spent a spinner with 3 equal sections, red, blue, and yellow, 2 times. Give a probability model for chance process, and then define event A as spinning a blue at least once. Okay, so pause the video here. I want you to come up with a probability model, work with a neighbor. We need a sample space and the probability for each event. And then we're going to define probability of A of spinning at least 1 blue. So go ahead and pause your video here and work this out with your partners. Okay. Hopefully you came up with this for your sample space. 2 reds, a red and a blue, a red and a yellow. 2 blues, a blue and a red, a blue and a yellow. 2 yellows, a yellow, blue, a yellow, red. So there is our sample space. And then we need to find the probability that each event happens. Well, we have 9, so our probability here would be 1/9. Okay, part B then wants us to find the probability that we have at least 1 blue. All right, so go in there. Everywhere there's at least 1 blue. There's at least 1 blue. Here's at least 1 blue. So everywhere you see a B. So it looks like we have 1, 2, 3, 4, 5. So our probability should be 5 out of 9. Okay, Mrs. Chevette keeps a mystery box in her classroom. If students meet expectations for behavior, they are allowed to draw a slip of paper without looking. The slips are all of equal size, well mixed, and have the name of a prize written on them. Here's the probability model for the prizes a student can win. Explain why this is a valid model. And then after you're done with that, we want to find the probability that the students won't win extra recess time. So what is the probability that they won't win it? Okay, so again, let's pause the video. We're going to work with our partners and come up with our answers for A and B. Well, for A, as I'm looking at all of them, I see that all of the probabilities are between 0 and 1. And then we're going to add them all up. Sorry. We're going to add them all up. So grab your calculator, 0.4 plus 0.25 plus 0.15 plus 0.15 plus 0.05. What do those all add up to? And I think if we do it correctly, they should add up to 1. So that is why we have a valid probability model. So we need to say that all probabilities are between 0 and 1, and then they add up to 1. Okay, part B then wants us to find the probability that a student won't win extra recess time. So they don't want that one right there. So let's use our complement or our opposite problem. So we're going to do 1 minus the probability that they do get extra recess time, which is 0.05. So the probability of not getting extra recess time would be 0.95. And I forgot to write the name up in there. Did you get it? All right, let's try one more. According to recent U.S. Census Bureau data, the number of people in U.S. households have the following probability model. Suppose that a household of 5 or more people is considered a large household. Randomly select a U.S. household. Part A says find the probability that the number of people in the household is 4 or fewer. And then part B, find the probability that the chosen household is a large household. Okay, again, pause your video and find your neighbor and work it out. Let's see what we get. Okay, so for part A, you can either do the complement problem or you can just add them all up. Whatever one you want to do is good. Sorry. So we want anything that is 4 or fewer. So I could just add up these 4 together, or I could do the opposite problem and take 1 minus these 3. It's going to give you the same answer either way, so whatever way you want to do it is good for you. So we want the probability that we have 4 or fewer. So again, either method. I'm going to do the opposite problem on this one. Actually, no, I won't. I'll just do 0.28 plus 0.34 plus 0.16 plus 0.13. Now that's going to give me the exact same answer if we did the opposite problem, 1 minus the probability of not being 4 or fewer. So if we added those all together, I got 0.91 on mine. And if we did the opposite problem, I would have added 0.06, 0.02, and 0.01, and you would get 0.09. So the opposite of that would be 1 minus 0.09, which also gives you 0.91. Okay, there's part A. Part B, find the probability that the chosen household is larger or is considered a large household. So that is anything that is 5 or more. So on this one, 5 or more would be these guys right, which we literally just added up in our opposite problem just a little bit ago. So the probability that it is a large household will be 0.06 plus 0.02 plus 0.01, which we know is 0.09.